All right, guys, today we are going to talk about some special bases for exponentials and log functions. And so first, let's talk about E, right? What the E? So you guys have seen this before a couple times. I haven't gone into it in depth, but what is E? What is it all about? Why do you keep seeing it come up? Well, E is a very special number in mathematics, right? E is an irrational number. That is, you cannot express it as a fraction. All right, it's kind of like pi in that it's an infinitely long, never-ending, never-repeating decimal. E is equal to 2.71828, and so on. As I said, it goes on forever. It doesn't repeat, though, right? And it can't be written as a fraction. So where does E come from? Well, originally, when we think about the definitions for E, oftentimes we think of it as coming from an application, all right? And that application is a compound interest formula. That is, compound interest, right? The amount after time t, right, after a certain amount of time, is going to be equal to your starting amount times 1 plus your interest rate over n raised to the n times t power. Now, this is just a alternate form of simple interest where n represents the number of times that you might calculate and add in interest into account. So the number of times, we actually call that compounding. The number of times you compound interest in whatever time period t represents. So for example, if t is in years, then that means your interest rate r is in years, and n would be how many times per year you would compound interest. Well, the interesting thing happens that as n gets bigger and bigger and bigger and bigger, it kind of levels off, right? So first time you start compounding interest, if you compound interest just once a year, the amount after a certain, time period is going to be equal something. If you compound more often, that means you calculate interest and add interest in, and then in the next little time period, more interest grows on top of that. That's compounding. Compounding more often will actually increase the amount of total value that you have in that account over that t years. The problem is that it levels off. So, compounding twice a year and then 3 times a year and then monthly and then daily and then hourly, it doesn't keep growing to infinity. It kind of levels off. And what that levels off to is E. That is, if we compound continuously, we would get the formula A is equal to P0 E to the RT. All right. Now, this isn't really a definition of E, but this is one of the first places that it kind of comes up in math and applications. To actually do definitions for E, we need calculus. All right. And the calculus definitions come, the first one kind of comes from that formula. Basically, as n goes to infinity, that is, as n gets larger and larger and larger and larger and larger, 1 plus 1 over n to the nth power ends up being equal to E. You could actually plug in values in here for n, larger and larger and larger values for n, and see that it is going to be equal to about 2.71828. Now, also, sometimes if you consider f of x being equal to 1 over x. That is, you take a look at the graph of 1 over x, which we've done before, which has that horizontal and vertical asymptote. And if you calculate the area underneath it and add up as much area as you possibly get, so that the area of that shaded region underneath here, I'm kind of drawing in blue for that shaded region, and we chop it off and stop it right there, that area will be equal to 1 if this value that we end at here is E. All right? So that's kind of a second definition. Again, in calculus, we take a look at calculating that area underneath the curve. Right? The third definition, okay, here we go. So the third definition of E is that if you were to add together 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and you did this on and on and on and on and on forever, adding together all of those fractions together, you would get E. This infinite sum ends up equaling E, which is kind of unique. So now, this base E, again, what do you need to know? Do you need to really know these definitions right now in Algebra 2? No. What you do need to know is that E is an extremely special number in mathematics and calculus for talking about the growth and proportional growth of populations and so on. We use it a lot there, use it with normal distribution curves. We use it in a lot of different places, and so we've named it a special letter E, just like we named pi, because that's so useful to us, right? Know that its value is 2.71 approximately. That is, so it falls in between 2 and 3. It's irrational like pi, but it's something that you're going to see come up often because it is a special base for us to use with exponentials and with logs, okay? So special notation for those logs and exponents that we need to know. Notation. All right. First, is ln of x. All right. So anytime you see ln of x, sometimes when it's printed out on a computer, that L almost looks like a 1, but it really means ln of x. You have ln of x on your calculator. Usually there is an ln button. Right next to the ln button, you normally find e to the x, because ln is the inverse of e to the x. This is a log with a base of e. So in other words, we do not write log base e of x, right? That's not the notation that we use. We do use natural log of x for a base of e. The second special base that you should know is if we ever write log of x and we leave the base blank, that is, we do not write a number down there, if you ever notice the base missing, then it's understood that this base is 10. And this is what we call the common log. So in the problems that you're going to be working on, you are going to be seeing both this natural log, is what we call ln of x, and this common log. All right? Especially getting through with natural logs, you will see problems, for example, like what is the natural log of the 5th root of e squared? All right, something like that, which of course is going to be 2/5, because this question, this log, wants to spit out the exponent. Its base is e, and it's asking us e to the what power equals the 5th root of e squared. And so this brings me to a property of inverses that I think I went over the other day, but we're going to review it again here. And that is that inverses undo each other as long as you're nicely defined. That if f and g are inverses, and nicely defined, that is, x is in the domain of each, then f of g of x is going to be equal to g of f of x, and these things are just going to undo each other and cancel each other out and just give you x. That's in general for kind of any inverses, and so you are going to see come up problems like natural log of e to the fifth, right? So you raise e to the fifth, you get some number. That's 2.71828 to the fifth. Then the natural log says, okay, e to the what power equals that number? Well, it's just 5, right? They're going to undo each other and cancel each other out. How about log base 3 of 3 to the x squared? Well, whatever you plug in for x squared, you raise 3 to that power, then you say 3 to the what equals it, well, it's going to be equal to that power of x squared. And so these two things kind of undo each other. We can compose in the other direction. 10 to the log of 50. Well, of course, this is a common log. I didn't put a base there. So the log spits out and says, okay, 10 to the what power equals 50? Well, 10 to the something equals 50. I don't know what that's going to be. In between 1 and 2, you would get an exponent that would equal 50. Now raise 10 to that power. 50 is going to come out, right? We just said 10 to the what equals 50. Now raise 10 to that power. You're going to get 50. So notice how the exponential 10 to the power and log base 10 kind of cancel each other out, leaving you with just 50. Problem is you need to make sure you are defined. So when I write log base 3, or I'm sorry, if I write 3 raised to the log base 3 of -9. Well, 3 to the what power equals -9? That's impossible, right? This here does not work. It's not just going to cancel out and give you -9 because that is undefined for -9. So the whole thing is going to be undefined. All right, so be careful taking logs of negative numbers. And now you know about some of our special bases, as well as this idea of composing inverses. Okay? Try the practice problem today, and I'll talk to you soon.